Hey everybody, so the topic today is estimation. The idea here is that we have some observed data. Somebody gives you a data set, and you want to estimate the right parameters theta to describe the distribution. Inherent in this viewpoint is the idea that you already have a model of this data. You know what the right distribution is to describe the data. Okay? So that's critical here. So this works best when we have a theoretical reason to suspect that this data will be distributed by a particular form. Okay? We have our classic coin flipper. We know that the probability that a particular coin comes up heads is described by a Bernoulli distribution. And we know that the probability of how many heads we get when we flip a coin a certain number of times is described by a binomial distribution. This is the stuff you learned in stats class. So what if we get the example that we see on the screen? If you flip a coin 3 times and get all heads, what is the probability of heads of this coin? What's the theta that we want to use to describe a Bernoulli distribution or a binomial distribution? Well, if you were a frequentist, you would say that the probability of heads is 1, because the observed empirical data is all heads. So the most likely estimate is it's a perfectly biased coin for heads. The funny thing is that even with a fair coin, it's not that unusual to get a run of 3 or 5 heads, right? This is a reasonable thing to happen even with a fair coin if you flip coins long enough. So if you're a Bayesian, you might want to have a prior belief about the coin and integrate the data you're observing and that prior together to form a posterior estimate of the model parameters theta. Okay, so we're going to do both. But to get to both, we need to give a little bit of framework. So here's our framework. We need to understand the expected value of a distribution to start with. And this is just the average, right? This is the mean that you're used to. It's the weighted sum of the probability of every possible element in the observed data multiplied by that particular data point. So for a discrete distribution, it's described in discrete terms. For a continuous distribution, we've got to integrate over the area instead of sum over it. So let's think about that coin flip. So the Bernoulli distribution is parameterized by this theta, where theta is the probability of heads. Right? So when we have a run of n coin flips, then each coin flip is statistically independent of the previous ones. So we know the probability of getting a set of coin flips is just the product of the individual Bernoulli trials. Okay? So what we want to do to get the maximum likelihood estimate, or the frequentist view of the parameters, is we can essentially optimize to find the value theta that best fits the data that we observe. Well, how do we optimize? The best way to do it is to take the derivative of the thing we're interested in, and as long as the thing we're interested in has a particular form, we know that there's going to be one and only one maximum, and we can set that maximum so the derivative at that point will be, the derivative is going to be 0 at a maximum, and so we set the derivative of the thing to 0 and solve for the value that maximizes the likelihood function. Now, how do we do this? Well, we had a product, and that makes it hard for us. So if we take the natural log of the likelihood function, this is a so-called log likelihood function. It is literally the likelihood function thrown through a logarithm. And the great thing about logarithms is they turn products into sums. So we can remove that product, and that makes it easier to do the derivatives, as you can see on your screen here. Right? All we've got to do is set that derivative equal to 0, which essentially lets us set this term equal to this term, and then move things around until we can do a bit of algebra and solve for theta. And it just turns out that the maximum likelihood estimate is exactly the expected value of the distribution, which, as you know, if you sum up a bunch of ones and divide by the number of ones you've summed up for, you're going to get an expected value or maximum likelihood estimate of 1. So this is the summary on maximum likelihood estimation. We're trying to find a parameter theta which maximizes the likelihood function. We're going to do it by finding the value of theta which maximizes the likelihood function. And the method of doing that is just like, least squares estimation, which you've hopefully done in a previous class. We make it so that we know for a fact this thing is convex, so that we can solve for where the derivative is going to be equal to 0, and that turns out to be the expected value of the distribution. Just some notes on notation. You will sometimes see theta star or theta with a little circumflex or hat on it. Those mean this is the optimal parameter. This is an estimate of the optimal parameter. Okay, so that's maximum likelihood estimation. What does it mean to do this using Bayesian estimation? Well, we have our familiar version of the Bayes equations. We have the likelihood function, which is the same as what we were just looking at under the frequentist view. And in fact, the frequentist view is really just thinking that the likelihood of the observed data is everything. But the Bayesian version of this is to multiply the likelihood by our prior beliefs in what the model should look like. And then, of course, we have to normalize it by the marginal likelihood. Now, because the marginal likelihood down here is something that we don't largely care about, we're interested in the particular parameters of the model, and this is a constant, we oftentimes talk about the posterior just as being proportional to the numerator, and we ignore the denominator because it's a constant. Okay? So this is the form of Bayesian estimation. We now not just have the likelihood function, but we're also integrating our prior. So while we're trying to figure out what prior should we do, we talked about this previously, right? Priors reflect beliefs or potentially previous data. But we're looking for a prior that makes sure that our posterior distribution is the same family as our prior. When we have a situation where we have a prior matched up to a particular likelihood that generates the same posterior as the prior, those are said to be conjugate distributions. We don't like it when the prior gets multiplied by the likelihood and we end up with a brand new kind of distribution in the posterior. That makes life hard. So we generically prefer to work with conjugate priors. Now it turns out that all members of the exponential family of distributions have conjugate priors. And our binomial distribution is a member of the exponential family. So how do we know that the binomial is a member of the exponential family? Well, you've probably hopefully seen the binomial distribution before. It's the number of combinations with n, the number of trials, number of coin flips. Choose the number with n over x, where x is the number of heads that we get, right? So number of trials, number of heads. And this is the probability theta, the probability of heads, probability to the power of number of heads, 1 minus the probability times the number of trials that came up as tails, right? And if you do the log trick and a little bit of algebra, you can see that this thing comes up in the form of an exponential of a logarithm, where this logarithm of p over 1 minus p is the exponential parameter. So not to belabor the point, but I just wanted to show you that a binomial distribution is indeed an exponential. So if you go back here, if you look at a binomial likelihood function, that is our 3 coin flips, the prior and the posterior for those that are conjugate with a binomial is the beta distribution. Okay, to talk about the beta distribution, well, a random variable has a beta distribution with these parameters, alpha and beta. And it has this form where we have this gamma function, alpha plus beta, over gamma of alpha, gamma of beta. This whole thing is a freaking constant. Okay, I'm going to talk about what gamma means in just 1 second, but this is a constant. So this looks mighty familiar, doesn't it? Exponential family. X to the alpha minus 1, 1 minus x to the beta minus 1. So again, this whole thing is a normalization term. And the expected value of a beta distribution is alpha over alpha plus beta. All right, what is this gamma function? Well, it's really just a generalization of the factorial that can be used on not just integers, but real numbers in between the integers. Okay? So gamma, when we feed it integers, is the same as x minus 1 factorial. Okay, so here's our beta distribution. It's got these parameters, alpha and beta. And what we end up seeing is that these parameters give us very different shapes. So maybe to note, when you have alpha and beta equal to the same number, so this is 2 and 2, you get a distribution that is symmetric. If you have numbers like more alpha than beta, then we end up with different situations, like this orange thing here. Nope, whoops, sorry, I did that wrong. That's more beta than alpha. So more beta biases us to the left-hand side. More alpha is the blue line, now that I've paid attention to what I'm doing, and it biases us to the right-hand side of the distribution. Where again, what is this? This is the probability of heads on the x-axis. Okay. By the way, special case, beta of alpha equal to 1, beta equal to 1, yeah, that's a uniform distribution straight across at the 1 here. Oh, sorry, I guess, yeah. So that's where we're at. So beta is conjugate to binomial. So what happens is when we multiply the binomial likelihood function by our beta prior, then we have this situation. Here's our binomial, yeah? Here's our beta distribution. Our binomial is parameterized in terms of the number of flips we did and the number of heads we've got out of that flips. So n is flips, x is heads. Our beta is parameterized in alpha and beta, or A and B, I guess, is how I've got the notation in right here. My bad. Okay, remember this thing here, it's just a constant. It solely exists to normalize the beta function. So let's get rid of it. Throw it to outside this. And instead of saying this is equals, let's say this is proportional, because it's going to be multiplied by this normalization. Oh, look, 2 exponential style families multiplied by each other. Something to the x power, something to the a minus 1 power. Well, the thing about exponential family stuff is that what is multiplications in flatland is an addition in logland, right? So theta to the x, theta to the a minus 1, it's just theta to the x plus a minus 1. And 1 minus theta to the n minus x, 1 minus theta to the b minus 1, it's just 1 minus theta n minus x plus b minus 1. So we've maintained the same format, the same exponential family format. And we've gone from a beta prior, multiplied it with a binomial likelihood function, and come out with a beta posterior distribution in the end. And effectively, what we've done is we've just added a minus 1 samples of heads. And we've also added b minus 1 samples of tails to the data set. That's all we've done. The beta prior is just taking the place of us imagining a trial that didn't happen with a minus 1 heads and b minus 1 tails. Okay, so this is a view. I'm just going to leave it in the slides for you, which summarizes that thing that we just went through, where it shows you how really you can just imagine these as constants on exactly the same exponential family. They're just different constants. Okay, I'm just a recapitulation of what I just did. So the thing is that different priors lead to different posteriors. Remember that we have this just adding a minus 1 heads and b minus 1 tails when we have our prior. So if we do a beta 1, 1, that is a unique distribution. It makes a uniform distribution. That is, it's equivalent to saying, I don't know what to expect, right? We call this an uninformative prior. We don't know what to expect. We essentially are discounting the prior and making it go away. But on the other hand, if we did a beta 2020, remember those are symmetric distributions when a and b are the same on a beta. So this is going to be a strong preference for a 50-50 coin. It's going to be a relatively sharp thing centered at probability of heads equal to 0.5. Beta 10-1 is going to be a strong preference for the heads. Okay, we're going to be leaned over and have a long left tail. So that is that. Thank you very much for your attention. We're going to do a lot more examples of this sort of stuff in class.